All right, well, I'm going to start, even though the room here at UMass is just beginning to get people in it because we had a delay till 10 o'clock. So, but let me just say a couple words and we'll get rolling here. So, basically, as a review, basically we've used the equivalence principle to get T mu nu as a source. And we use that to get the gauging of the Lorentz transformation. So we gauge that. We also used it to get the metricity condition, this d alpha g mu nu equals 0. And we use that to get the connection. So basically, we've got all the ingredients out of this. We then have written out an action integral d for x square root of minus g minus 2 over kappa squared times the curvature plus L matter. And we get out of that, right at the end, last time we got Einstein's equation is r mu nu minus a half g mu nu. R is 8 pi g t mu nu. And from this guy, we got box phi is equal to 0, with box being this modified version with the derivatives acting on g also. And lastly, out of the same piece, we get T mu nu is 2 over square root of g, variation of the action with respect to g mu nu upper. Okay? So there's our big successes. So today I have a bunch of field theory things, a little bit more finishing up with gravity, and maybe we'll move into the weak field limit towards the end of the day, to the class. Okay? Any questions before I get going? No? So the first thing I just want to do is I want to add in the cosmological constant. I will add it in at this time. If we're doing an invariant, we also have the following. We could have the action being integral d4x square root of minus g minus lambda minus 2 over kappa squared r plus the matter piece. The volume element is invariant. A constant is obviously an invariant. So this is perfectly good also. The equations of motion that follow from that just follow from varying root g. And so without too much ado, it's r mu nu minus 1/2 g mu nu r minus 8 pi g lambda equals 8 pi g t mu nu, and there's a g mu nu there, sorry, let's see if I can get that written better. So this is the new piece here. You most often see this written with little lambda is 8 pi g big lambda. And you also often see this thing written with this shifted to the other side. So you can think of this as it becomes T mu nu plus, sorry, T mu nu plus lambda g mu nu, which gives you the interpretation that you'd expect. Lambda is a shift in the energy momentum tensor. That's a constant. That's the energy when matter is not around. The value of lambda is about, if I did my numbers right, it's 2.3. The 10 to the minus 3, I know. Electron volts to the 4th power. The if you take the trace of this, so let's take T mu nu equals to 0. So let's take out the matter. You take the trace, meaning dotted in G mu nu, you get R minus 2R equals 4 lambda, or there's 4 lambda then, or R is minus 4 lambda. So R mu nu in turn then is minus lambda G mu nu. So these are the highly symmetric spaces. Lambda bigger than 0 is de Sitter. Lambda less than 0 is anti-de Sitter. Okay. The sign of the Einstein-Hilbert action, the minus 2 over kappa squared, that sign is a convention. We had a choice when we were forming the curvatures. We started off with R mu nu alpha, well, let's see, R mu nu alpha, and one of these was up, beta, and we contracted mu beta to get our curvature. We could have contracted nu beta if we'd wanted to. That's the difference in sign. So there's a convention that you could just put in there. However, the sign convention on lambda is less fixed. To remember the sign on lambda, you do the following. Basically, remember that the Lagrangian, so the Lagrangian goes like here, like minus lambda. The Hamiltonian then, which is PQ dot minus L, should go like plus lambda. So lambda being a positive number is a positive energy density. Okay, so one always thinks of the cosmological constant as the energy and momentum of space with a positive sign, and so it should be minus lambda there. Though I have to admit, in my own papers, I often screw up that feature. You just write it lambda there. Anyway, that's sort of completing that part of the derivation. Any questions about that? All right. So now there's a few things I want to do now that I don't need to do right at this moment, but I'm going to need later in the course, and we might as well see it now. So, first one is something that Rob Caldwell, I think it was, up in Dartmouth asked about before. This is the first order or Palatini formalism. That's not a T. Okay, so let me just first do it for E and M, and you'll get the picture. In this first order formalism, you treat, in E&M, you'll treat F mu nu and A as independent fields. Independent variables. Okay. Then we would write out the Lagrangian as minus a quarter F mu nu plus 1/2. Well, I have to couple the two of them together. D mu A nu minus D nu A mu. That's a unique way to couple them together. And you minus E, well, minus A mu J mu. Okay. So
when you do that for
yep.
Wouldn't you like maybe want a kinetic term for F mu nu? So why not include derivatives of F mu nu? I mean, if you don't know that F mu nu is going to end up being the antisymmetric derivative of the gauge field, then
Right.
why not introduce terms that are first derivatives of the field strength tensor as like kinetic terms?
Yeah, it's a great question. And I think the answer is that if you're being general in this modern era of effective field theory, you would in fact do that. You would allow higher order terms. And so if we're now thinking about doing it for general relativity, there probably is some, when we get down to it, some difference between doing it the way I'm just going to do it, which reproduces usual Einstein, and what you would do if you allowed higher order terms. I mean, I think the answer is really that when first done, this was done to reproduce E&M.
Right. I'm just talking about it from like a symmetry perspective. If you want to treat, the F and the A as distinct fields, then why not include, kinetic terms for both of them, all possible couplings between the two of them, and also all possible couplings between the fields and external sources as well.
It sounds like a good idea. People here in the room, did you hear the question? Okay, so the question is, I've written out what in a minute is going to reproduce E&M. But if you just looked at this as a starting point for a field theory, normally in field theory, you're supposed to write out all possible couplings. Whatever is not forbidden by a symmetry is required. And so the question is, why don't you have derivatives of F mu nu? Why don't you have the F terms and the derivatives of A separately? I think the answer in general is if you were trying to do this in a systematic way, you would include all those terms. But that's not the way to reproduce E&M using this first order formalism. So roughly what I'm doing now is in some ways historical. I'm going to use this later on when I do fermions, is why I'm setting it up now. And when I do fermions, you naturally do get a field variable that's called the spin connection, which isn't immediately connected to the metric. There are initially two variables. And this first order formulation connects them. There's another way to connect them, which I'll do when I get there, but let me not give away that whole lecture yet. But I'm just trying to set it up now. Okay, was that Robert talking up there?
That was Damien. Robert hasn't been here for a few days, but yeah, Damien.
All right. All right, so let me just, shall I just head on?
Yes, please.
Okay, let me just do this out And we'll do it for general relativity, and then we'll come back. And by the time I do it again for real, we'll actually have effective field theory under our belt, and we'll ask the question again. Okay. But in this case, here basically the trick here is to then, if we take the variation of the Lagrangian with respect to f mu nu, there are no kinetic pieces, as was pointed out. You get minus a half f mu nu plus a half d mu a nu minus d nu a mu. So this gives us the usual connection between f and a, the usual dA. Okay, and then you take the variation of the Lagrangian, so d mu a nu minus the equations of motion for a nu, and this turns into d mu f mu nu equals j nu. Okay, so you've reproduced Maxwell by treating these things independently. Okay, if we do this for general relativity, when you do it for general relativity, you treat the connection mu nu lambda and g mu nu is independent. Actually I've saved this here. This is from last time. Let's see if I can move it up. Cut. Paste. There we go. Good. So when we're varying, if we take delta S, delta gamma mu lambda, you can sort of see where that happens. Remember, when we did the variation of R, we had a piece that was delta R mu nu, and R mu nu is composed out of gammas, and we wrote this as a total derivative. Okay, so in this case, we were going to set this equal to 0. The variation, then, you can see it sitting down here, is then I've got the integral d for x square root of minus g mu nu d lambda delta gamma mu nu lambda plus another term. Let me just not write that. The logic is what I'm after here. Okay, so this was the covariant derivative acting on this. Before what I did is, you see it down here, because we'd already had this condition, the metricity condition, that d mu on g gave 0, I said this is a total derivative, and I just dropped it. Okay, but now I don't have that connection yet. Now, by integrating this by parts, I get the condition, the equations of motion now, is that d lambda root g mu nu equals 0, which this is the metricity condition that I said before. You know, it's basically d lambda g mu nu equals 0, and that determined gamma in terms of g. Basically, that's the equation that determined gamma before. So now we've gotten this out by an equations of motion, and then the rest we do delta S, delta G mu nu, and we get the R mu nu minus 1/2 G mu nu R, where R is composed of gammas, which are now in terms of G. So this, by treating these two fields separately, restricting ourselves to only Einstein, we get back GR. Okay, so that's the first order formulation. And the question then will be, when we do this again, these will start off as independent fields, and I'll provide you with two ways to connect them up to usual physics. One of which is like the metricity condition, and the other which is this first order formulation. Okay? So this part over here is last time. Okay, good. Okay, another little piece of catch-up. This I don't use later on, but you might as well see it here, which is the boundary action. This is again, it comes from this total derivative piece. So recall there was the piece that's sitting right here. I can just pull it down here. Sits there. I just dropped it. Okay, and in field theory, we tend to be cavalier about doing that. But remember, general relativity is meant to be a theory of the universe. We don't necessarily get to decide whether there's a boundary in space-time or not. And many theoretical adventures now, like this ADS-CFT, have space-time boundaries where you have general relativity inside and a conformal field theory on the outside. And so if you're dealing with a boundary, there's a new piece. There's a new term that's needed to cancel off the total derivative term. Okay, so there's it goes by the name of York, who was the guy who did it, and sometimes Gibbons and Hawking. Which I just learned in looking it up on Wikipedia, did it about 5 years later. But they, of course, get their name on it then still. So basically, the boundary action, there's some boundary which, let's just keep the 2 over kappa squared there. There's the integral over some boundary surface. So this is a 3-dimensional boundary because the normal integral is 4-dimensional space. And there's some current there. Or sometimes you just see this written as minus 2 over kappa squared integral d3y, some k. So d sigma, the boundary is described by d3y times the normal. This is the normal to the surface. And without too much ado, I'm not going to really do much about it. So eta is normal to the surface at that point. We take the metric on the surface by taking out so this is a 3-dimensional metric. This lives on the surface. So it only has directions on the surface. Eta mu nu, eta mu, h mu nu is 0. That's the perpendicular condition. And then if I've copied correctly, since I've never derived this, S sigma is minus 2 over kappa squared integral d3y 2 h mu nu d mu eta nu minus gamma alpha mu nu eta alpha. Anyway, the main point of bringing this up is just to know that there is this guy. If you have to ever use this, you will have to learn more than I've just told you.
Wait, so are the etas their dynamical variables?
Well, the eta is it's not a dynamical variable, but it does change as you move along the surface depending on the shape of the surface. So, right?
Okay.
So if you had a funny shaped surface, the eta as you move along the surface, and h is a projection along the surface, and so I don't know.
So is this seems just sort of like maybe like a Gaussian curvature type?
Yeah, I think that's what it is.
Okay, is there a equivalent? What's the other one? The topological one. Is there a Gauss-Bonnet term?
I don't know the answer to that. I don't know the answer to that though. You remember in the Gauss-Bonnet term is of order second order in the curvatures. So there's probably a second order in the curvatures piece here too.
Oh, okay.
Okay. So I don't know how this I actually know nothing about how this gets supplemented if we go to beyond first order in the curvature. This is the piece that does, for the Einstein-Hilbert action, cancels the boundary term. It sounds to me like somebody's got a good research project. You can publish a paper to put the general quadratic action and find the boundary terms for that. Sounds like a good project. Okay. Next piece of trivia. Okay, so I'm going through a few little things about general relativity. Palatini boundary term. This is a curiosity. There's an alternate form of the action, the Einstein-Hilbert action. And it just comes from throwing away a total derivative in the usual action. And this one may make, I don't know, it's a curiosity as far as I'm concerned, but it actually feels interesting to people that do other types of nonlinear field theory. So to me in particular. So remember, R mu nu has derivatives on gamma plus gamma squared terms. Okay. The derivatives on gamma could be turned into covariant derivatives. So I could, it's not normally written that way, but I could write this as covariant derivative on gammas plus some gamma squared terms. There'll be slightly different ones. Okay, because that's all the change there is. But this covariant derivative terms are total derivatives. Okay, so you can throw them away or drop them using this boundary action. So you drop these. In fact, that's probably one way to construct that. I've never thought of it that way, but that's probably a way to construct this is you make this procedure and use that as the boundary action. But that means that you can be left over with just gamma squared terms, you don't need to have a derivative term. And so the alternate form is the following. Einstein-Hilbert action is minus 2 over kappa squared integral d4x square root of minus g. Now, so gamma gamma g minus gamma gamma g. Now let's fill in all the indices here, okay? And I have to look it up. So it's rho nu sigma mu nu. And the second guy is G mu nu. Mu nu is down on this index. Rho eta eta. There we go. Okay, I know. If you want a place to look up this, Tony Z's book has this in it, for example. I shouldn't make it seem like he derived it first. It's well known. To me, this looks useful. This is now, this type of a formula is dg with the indices rearranged. So it's like usual quadratic things. Derivatives of g, derivatives of g. And it's like other ones that we effective field theorists know. We have a Lagrangian that's f squared over 4, trace d mu u dagger. So these type of Lagrangians are very familiar to us. Nonlinear Lagrangians with 2 derivatives of the fields, of nonlinear fields. And that's what it basically is here. So I don't know if that helps anybody. It may just be a curiosity, but you sometimes see this. Okay. Next piece of field theory is I want to talk about energy momentum tensors in general. So what I'm going to do is the canonical energy momentum tensor versus a symmetric one. Okay, so this is a general quantum field theory stuff. I'm going to do it in flat space because it generalizes, but let's do it in flat space. And the place that I looked this up when this is where I learned it anyhow, is this Ixen-Zubair. Has a good discussion of this in the case of the photon. Okay, so we've done scalars so far. And scalars, we got T mu nu was, it was d mu phi minus 1/2 g mu nu phi squared. No, I'm sorry, d lambda phi. Let me drop the mass term because I'm going to drop it soon anyhow. That's the one that you get if you use Noether's theorem. Or if you use T mu nu is 2 over root g variation of Lagrangian with respect to g mu nu. It's actually square root of the Lagrangian. Okay. So if you do Noether's theorem or general relativity, you get the same T mu nu. But in general, they're different. So in general, if you have T mu nu, Let's do it. It's the variation. This is the canonical. D of d mu phi times d nu phi minus g mu nu L. Okay. In this notation, this is the symmetry associated with mu. So if I did T0 nu, that's the symmetry associated with time translations. And it's the current nu. So you would have d nu T mu nu equals 0 is current conservation. Okay, so if you do a scalar, you get what's above there. But now if I do a Dirac field, the Lagrangian is psi bar I gamma mu d nu psi, gamma mu d mu, sorry. Okay, so the variation of the Lagrangian in respect to d mu psi, yes?
Really quickly, the canonical form for T mu nu, you get that from the total from the total derivative term vanishing. That's the known term.
You get this from gauging the usual Lagrangian. So basically, you
do a space-time translation.
Exactly.
Okay, right. Okay, so if you do that to the original Lagrangian, then the original Lagrangian is written with covariant derivatives, not regular derivatives.
Yeah,
So
I'm
we
doing,
breaking down the SR form for the canonical stress energy tensor? If we're talking about general relativity now, why don't we use the variation, the derivative of the Lagrangian with respect to the covariant derivative of phi times the covariant derivative of phi?
that's probably the case, but at the moment I am really just doing flat space now. So.
Okay, so when you read general there, you didn't mean general relativity.
No. This is the general canonical form.
Okay, my bad, misinterpretation.
Yes, in general, canonical form, which is basically Noether's theorem. Okay. So Noether's theorem. So when I do it let's do it for the Dirac field, I get a gamma mu there, and so T mu nu starts out as psi bar I gamma mu d nu psi minus g mu nu L. And this guy's not symmetric. Okay. Likewise, if I'm doing the photon, we've got the Lagrangian is minus a quarter F mu nu. The variation of the Lagrangian with respect to d mu a sigma is minus F mu sigma. And so T mu nu starts out as minus F mu sigma d nu a sigma minus g mu nu L. So again, not symmetric. Okay. But in GR, you clearly get T mu nu is 2 over square root of G, variation of the action respect to G mu nu. That's obviously symmetric. Moreover, even if you're not doing general relativity, you'll most often see the energy momentum tensor for photons, for example, written out in a symmetric form. The form that I've written here is actually not what's most often used. Okay, and the reason that these both can be true is there's a non-uniqueness. And it's actually not that hard to see the non-uniqueness. Let's add to the Lagrangian a total derivative. Okay, so let's take it to be some d alpha, some function alpha of the fields. Okay, now since these things only are the fields, this is chi prime alpha d alpha phi. In other words, you use the chain rule. Chi prime is the variation of chi respect to phi, the derivative of chi respect to phi. Okay, so I've just added a function of the fields there. Okay, so this is total derivative. Okay, but then if I go back and look at the procedure for getting energy momentum tensor, I have a derivative of phi now from that total derivative. And so I get a change. This is then a change in T mu nu, which is chi prime mu d nu phi. Okay, so the derivative of this function as d mu phi, I've shifted the T mu nu by something that's also not symmetric. Okay. And so you then can make T mu nu symmetric by a particular choice of total derivative. In fact, there's a procedure for it, and that's the procedure I want to go through because it also brings in other good things for us. All right. So anyone have a question about just what I just did, adding this total derivative, changing T mu nu? Okay. Okay. We're guaranteed by this theorem that total derivative doesn't change the equations of motion, won't change the conservation law either, because it's just a function of the field. Okay. And if you'll excuse me, I'm going to take a detour now. The detour will be into angular momentum.
Hey, John.
Yes?
I'm sorry, I'm totally like spacing out here.
Okay.
Could you just quickly remind me, because I'm dumb, why we want the stress energy to be symmetric?
Well, so for general relativity, it comes out symmetric because you're differentiating with respect to a symmetric tensor. In usual field theory, you don't have to make it symmetric. The form that you have here for the photons, however, isn't so great because it's also doesn't look gauge invariant.
Yeah.
Okay. The symmetric one, however, is gauge invariant. So in fact, you know, what I remember from that Ichthyosin-Zubair discussion is they're saying, why doesn't the energy momentum tensor look gauge invariant? Here's how we can make it look gauge invariant, and oh, by the way, it comes out symmetric when you do that. So in usual field theory, you don't have to have it symmetric. And I don't know anything particular about the Dirac one that forces you to do it. But in general relativity, you want it symmetric.
So I was just wondering, maybe this is like leaping ahead a little bit, but then are the non-symmetric portion of the stress energy tensor, is that somehow related to the torsion then of the metric? Or
not of the energy momentum tensor. You'll see what I'm about to do is you're going to see that the anti-symmetric part is related to the spin current.
Okay.
Okay, which is why I'm detouring into angular momentum.
Okay. Cool. Thank you.
Okay. So again, at the moment, there's no particular urgency for in general relativity for doing this, but this is good old field theory. And I'm going to use some of this stuff that I'm about to tell you again when I do fermions. Okay, so let's go back to this Lorentz invariance. So remember that both Lorentz invariance and rotations can be done in the same formulation. So, you know, we've taken x mu to some x prime mu, which is lambda mu nu x nu. And if we make this infinitesimal, this lambda mu nu is delta mu nu plus some omega mu nu dot 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 x nu. Okay, so the infinitesimal translation, Lorentz transformation or rotations is in this omega. And omega, if you write it out, actually, omega mu nu, if I have the indices lowered, is antisymmetric. Okay, brackets is my notation for antisymmetric. Okay, what I haven't done so far is transform a spinor, for example. So when I transform a spinor, you also have to transform a spinor. So psi prime of x prime is 1 minus I over 2 omega mu nu S mu nu. In general, I'll come back and do this, but this is actually for general fields. If I could write out an S mu nu also for spin 1 field. For spin a half, S mu nu is sigma mu nu. Okay, and in general, so for fermions, but it's certainly the case, there's an algebra S mu nu commuted with S alpha beta. This is actually a more general thing, is I. Let's get the indices right. Basically, I'm in flat space, so it's A to S, A to S, A to S, A to S. These things are antisymmetric in both indices. So nu alpha, mu beta, nu beta, mu alpha. So that's the symmetry in alpha beta. Then there's mu alpha, nu beta symmetry in mu nu. and then mu beta nu alpha. Okay, so the sigma matrices satisfy this, but also in more general, this is a SO31 algebra. Anyway, that's perhaps not needed here. But if you do know this theorem, again.
Wait, sorry, John.
Yeah.
I haven't seen this in ages, so I'm totally blanking a little bit.
Yeah.
The sigma mu nu, those are the like.
Okay, yeah. Sigma mu nu. Sigma mu nu.
That's the Levi-Civita time.
No. Sigma mu nu is I over 2 gamma mu gamma nu.
Oh, okay.
I'm sorry. Yes, I should have said that. I will do a little review on this stuff again when I do fermions, because remember at that stage we have to gauge this. So we're going to be gauging not only the translations but this spin part here. Okay, when we do fermions. So I'll come back and do a little review of this. But these are gamma matrices. Okay.
Just like outline, how do you derive that form for the transformation?
Okay, yeah, so here's how you do it. Basically, what you want is you want the Dirac action to be invariant. So it's psi bar I gamma mu d nu minus m psi. Okay, we're going to make the coordinate transformations. So basically, psi prime is going of x prime is going to be some s times some psi of x, where s is a transformation matrix. Okay, since we're transforming the derivatives when we go to x prime, we have to transform the variables in order to make this an invariant. And basically, there's a condition. The condition on top of my head isn't exactly clear, but I think it's the following: S dagger gamma mu S is lambda mu nu gamma nu in general. Okay, and you can sort of see, so derivative transform, so gammas have to have some corresponding transformation. By transforming the spinors, you make the gammas transform the right way to get an invariant. Okay.
Also, this is only for the Lorentz subgroup of the Poincare group.
It's only the, well, it's also for rotations.
Right. Well, I'm including rotations and
yes, that's right. So it's for Lorentz and rotations. Yes.
Okay, so a similar thing can also be done for translations, and I'm going to guess, based on intuitions, that the gammas don't change under translations.
Yes, that's right. So gammas don't change under translations. But remember, to get the there's currents out, you have to let those translations be functions of x, and then you have to worry.
Yeah.
Okay. Okay. Anyhow, the general form of S is that can be done from a set of these infinitesimals. It's minus I omega mu nu over 2 sigma mu nu. That's the general transformation. All right. So that's this is really, it's derived from the invariance of the Dirac action under transformations. Again, the Ixison-Zuber book does a pretty good job on this one. I have to admit I learned it out of Bjorkane and Drell, but so I don't know who else does a good job on this, frankly. But the key feature here is that, Noether's theorem gives you a conserved angular momentum current. Okay, so M mu alpha beta. So the alpha beta is the translation, the thing that we're doing that involves rotations. Mu is the current index. Is x alpha t mu beta minus x beta t mu alpha plus some spin piece mu alpha beta, where this S mu alpha beta is minus I times the variation of the Lagrangian with respect to d mu psi times S alpha beta psi. Okay, by it, where S is up here. And it's gotten really by gauging the Lorentz transformation temporarily to get the Noether's current, and then you get the derivative from gauging that. All right.
Which
I'm sorry. Yes.
With? Which component do you take the divergence with to get the conserved current? I'm gonna assume mu.
Yeah, it's actually, I've tried to do it mentally in my head too. Let's. Yeah. Yeah, so why am I getting that piece?
I think it's mu that you have to contract with, because then you'd get like the standard R cross P.
Yeah, yes, no, that's right. So this is, let me say a few things. So the piece that you contract when you do the divergence is the mu. Okay, so that's the conserved piece. Was that what the question was?
Yeah.
Okay, good. I was trying to do the derivation for this thing in my head, and I wasn't getting it right. But the things that you can see, you can see the usual angular momentum piece here. This is the R cross P piece there, because T0 is the momentum. So if I have IJ there, I get XI PJ minus XJ PI. So there's R cross P. And this piece is the spin piece. It comes out like sigma mu nu. And if you do this for the Dirac piece, which again, these Bjorken and Drell and X's and Zubair will show you that you get spin a half. Anyway, this conservation here equation is, you can see since T mu nu is conserved, the piece that you get is you take the derivative here, you get delta alpha mu T delta alpha mu T mu beta minus delta mu beta T mu alpha plus the derivative of S alpha beta. So the spin piece isn't conserved by itself. You've used here the derivative T mu nu is 0. Okay, but this then tells me that the antisymmetric piece alpha beta of T mu nu is minus I over 2 times the derivative of the spin piece. Okay, and the thing I didn't say is the T that comes out here is this canonical one, the one that comes from Noether's theorem. So let's just call it canonical. Okay, so the one that comes from Noether's theorem comes out there. So the antisymmetric piece is connected to the derivative of the spin current. And so these pieces that we get here, that if I made that symmetric by adding and subtracting something, the difference is the antisymmetric piece of that and the antisymmetric piece here would be the derivatives of the spin current. Okay? So there's the construction. This then leads to yet another construction, which is constructing the symmetric one. So this is goes into the name Belinfante. Okay. So basically, constructing the symmetric energy momentum tensor. So the Belinfante T mu nu is T canonical mu nu plus 1/2 d mu times this, no, d alpha spin alpha mu nu minus spin mu nu alpha plus spin, it looks like nu alpha mu. Okay, so if I've done this construction right, actually, looking at the clock, I'm going to skip some stuff here, but if I do this construction, the Belinfante's antisymmetric piece is 0. I've basically just added pieces up here that cancel off that just by using that relation. And this is still conserved, so d mu T Belinfante mu nu is still 0. The derivatives up here, the second piece, the derivatives cancel. So by doing this construction, we have the symmetric tensor from general relativity. Okay. So
what are all these extra terms?
These terms here, these are the terms that you add. You have to add to the canonical piece to give you the symmetric energy momentum tensor.
No, I know that, but like, what do they do to the equations of? Oh, they're total derivatives, so they don't.
They're total derivatives. Exactly. Okay. That's right. So there's a choice of a particular choice of total derivatives that you've added to the Lagrangian.
So these extra pieces, these extra total derivatives that we're adding, they can play a major part on the boundary.
Presumably, but this is for the matter action, so you'd also then be changing the matter action on the boundary. Yeah, actually, that's not necessarily right, because we don't do general relativity with the with the symmetric energy momentum tensor, you don't have to modify the Lagrangian. This would be if you were not doing general relativity and trying to get it from this theorem.
Wait. So the Belinfante stress energy.
Yes.
You're adding terms to the stress energy. What terms do we have to add to the Lagrangian to get that stress energy?
Okay. So it depends how you define your stress energy, your energy momentum tensor. From the Belinfante is the one that comes from the variation of the action with respect to g mu nu. Okay, so if you're doing general relativity and using this as your definition, you don't have to do anything. Okay, if you're doing flat space field theory and you wanted to get a symmetric tensor instead of the canonical one, you would add something which I don't know what it looks like, but. Okay. Okay. Last topic for today, if I can squeeze one more in, let me do the improved T mu nu for scalars. Okay, so what I was doing up above there is the T mu nu for spinning particles. Let's consider the following. The Lagrangian is, I'm doing this for massless fields, d mu phi minus. So normally for massive fields we have a half m squared phi squared sitting here. We could also add a term in here that's the curvature times phi squared, and for a scalar field it's over 2. Okay, so this is your usual curvature, which remember goes like, so R goes like 2 derivatives of the metric. So dimensionally, R has dimensions of 2 derivatives. And so if we're allowing 2 derivatives on phi, you should allow 2 derivatives on the metric also. At the same order in the derivative expansion. The T mu nu that you get out of this, so if I take this, okay, so let me say a couple things first. This R has terms in it that's 2 derivatives on 1g plus derivatives of g squared. So this is the gamma squared, and this is the derivative of gamma. Okay, so if I take T mu nu in general relativity from this, it's the usual, the canonical. But then there's a couple extra pieces. There's a piece, the obvious one is minus C R mu nu minus 1/2 G mu nu R phi squared. But then there's also a piece which is C G mu nu box minus d mu d nu phi octagon phi squared. Okay. In flat space, this guy vanishes. But the second term doesn't. Okay, it's a total derivative on t, but it's still has matrix element. So if I take some, let's take k, t mu nu, k, and I only actually have this written down for a massless field, so let's drop the m. It's k mu, k prime nu, minus k nu, k prime mu, minus g mu nu, k dot k prime. That's the usual piece. And then there's a piece here which is 2c q mu q nu minus g mu nu q squared, where q is k prime minus k. So this changes the energy momentum tensor, and it changes, there actually are real changes associated with this. So for example, if I take k eta mu nu, t mu nu, I'm in flat here, k prime. That should be a plus. Again, I'm just going to skip to the answer. It's just algebra. Minus 6c minus 1/6 q squared. Okay, I've used here k dot k prime is minus q squared. It comes from squaring this relation up there. Okay, so this, in this particular form, c is equal to a sixth, implies that the t mu nu is traceless, t mu mu is 0, and this plays a role in anomaly discussions. It's coming up later.
Wait, but that's not what we want, like under FRW, right? Because like we want it to be what, like rho plus 3p for the
yeah. So actually in FRW, this q squared would effectively vanish. You're not carrying any momentum through the energy momentum tensor. So this last piece actually doesn't contribute in FRW. Okay, let me just give the reference here. There's a classic old reference for this, which is a Callan-Coleman Jakiv, and improved is the way you refer to it. But this plays a major role in conformal theories, because in conformal theories you want this to be traceless, so C is the conformal coupling and C is equal to 1/6 is a special value. All right. Anyway, it took a little longer to set up all these things than I thought. What we're going to do is come back. I will do the weak field limit. First thing, I'll show you how this really is gravity, and then we'll do weak field limit, and we'll continue from there. Okay? Good. Thanks.
Thanks,
Bye-bye.
Sean.
Yep, bye-bye.